Okay, so in the last video, we talked about recovering original signal from its sampled version. Okay, when that's possible, what conditions we need for that to be possible. But a lot of our analysis was in the frequency domain. So in this video, I want to look at what's happening in the time domain. So this is going to be about sampling, reconstruction in the time domain. Okay. So let's look at this. So let me just remind you of the block diagram for sampling. Okay, well, I start with my x of t. I'm going to multiply it. Remember, that's just our symbol for multiplying the two signals here. I'm going to multiply it by my impulse train. That has sampling period t sub s. Okay, what I get out is my sampled signal, x sub s of t. Then I'm going to put it through an LTI system. Okay, and I'm going to get out my y of t. All right, so that is our block diagram here, and I'll just make a note that the sampled signal is x of t times s of t. That is that symbol there, that circle with an X in it, and my output y of t from the LTI system, of course, is the input, x of s of t, involved with the impulse response, h of t. And in the last video, if you remember, we used a particular frequency response for that LTI system, and it looked like this. Okay, we had negative omega sub c, the cutoff frequencies. It had height t sub s, and that was my h of omega. Okay, so let's see what's happening in the time domain. Let's take the inverse Fourier transform of this function, which of course is just t sub s times a rect function. And that rect function, we want it to be 1 from negative omega sub c to omega sub c. Okay, and so of course that means this rect function is just going to be omega over 2 omega c. Okay, this is my h of omega. Why is that the case? Well, if I plug in plus or minus omega c here, this argument becomes plus or minus a half, and that is where these left and right sides of the rect function come down. Okay, so that's an easy way you can always check that. What's the inverse Fourier transform of this? Well, this would be good practice, okay, using the sinc and rect Fourier transform pair. But if you remember this 2 omega sub c in the denominator, that tells us that the sinc function is going to have frequency omega c. And the Fourier transform of this function is just pi over omega c times this rect. But I want the constant to be t sub s. So what should I multiply this by to get t sub s? Well, I should multiply it by t sub s times omega sub c over pi. All right, if I multiply that by the sinc function, then that will multiply this constant I get from the Fourier transform of sinc, and that would give me the constant I want, t sub s. Okay, so that is the inverse Fourier transform of that function, and of course, this is my impulse response, h of t. All right, let me just clean this up a tad. Okay, I'm going to use that t sub s as 2 pi over omega sub s. Okay, because then I can write this as 2 omega c over omega sub s times sinc of omega c t. Okay, just plugging in for t sub s right there. Okay, so now, for the purposes of this video, let's suppose we have all the conditions from the last video for perfect recovery. That's the case we're going to be looking at in this video. And so what does it mean to have perfect recovery? Well, that means this y of t actually equals my original x of t. Okay, so in other words, y of t equals x of t, and of course that's for all t. Okay, that's what perfect recovery is. So that's what we're going to be looking at in this video, but we want to see what's happening in the time domain. Okay, so let's look at that function y of t in the time domain. We know that it's our sampled input convolved with our impulse response, h of t, that we just found. So this is x sub s of t convolved with h of t. Okay, but what is our sampled signal? Well, it's just our original x of t times our impulse train, s of t. This is x of t times s of t involved with h of t. Let me just plug in for what that is. We've seen this before. Right, this is just the big sum of all the deltas from the impulse train. but each delta is scaled by the value of x at that location of the impulse. So x of n t sub s. We saw this in a previous video. And we're convolving that whole thing with h of t. Okay. What happens now? Well, we can use the distributive property of convolution to say, oh, I'm convolving this with a big sum. That's just the sum of that h of t convolved with all the individual components. So we're going to get x of n t sub s times h of t convolved with this delta, but we know convolving with a shifted delta just shifts my original function. Okay. So now let me plug in for what this should be, and it's just going to be right up here, h of t equals this function. I just have to plug in everywhere I see t, I have to plug in t minus n t sub s. So I'll do that now. So out front, I get the 2 omega sub c over omega sub s. That's me right there. Okay, times this sum. Negative infinity to infinity of x of n t sub s. And now I have that sink of omega c, now t minus n t sub s. Okay, so I just plugged in this argument everywhere I saw the argument t. Okay, so that's what we get. And now I want to look at a specific special case of this. So let's just recall real quick. This is going to be a nice special case. Recall what did we need for that omega sub c? We just needed it to be in that gap between the triangles, if you recall from the last video, which meant we needed that condition to be true. And so let's actually look, just for the purposes of this video, because it's going to turn out nice in the end. Let's look at the nice limiting case of when all those inequalities are actually equality. Okay, so it's sort of a limiting case, but let's look at it anyway. So let's say omega sub m equals omega sub c equals omega sub s minus omega sub c, or sorry, omega sub m. Okay, so what does that mean for the relationship between omega sub s and omega sub c? Well, you can see omega m equals omega c. So omega m here would equal omega c. So then I just have omega c equals omega s minus omega c, bring the omega c to the other side, and just get omega sub s equals 2 omega c. Okay, so I'm going to have omega c equals omega sub s minus omega c, bring that over there. Omega s equals 2 omega c. Okay, so that is the limiting case we're going to look at for the purposes of this video. And it's nice because look at what it does for us. Now this 2 omega c actually equals omega sub s, so that constant goes away. We're going to have x of n t sub s, sink. Okay, and now this omega c is omega sub s over 2. But remember, omega sub s is 2 pi over t sub s. So omega s over 2, the 2 cancels, and I'm just left with pi over t sub s, t minus n t sub s. Okay, so we get this formula for our output y of t. Sometimes it's called an interpolation formula. Why is it called that? Well, if you remember, we have perfect recovery. So this actually equals what? Well, remember, y of t equals x of t. So this actually equals x of t. Isn't that crazy? The sum of all these sinc functions scaled by these values, that equals x of t. And it turns out it does. Let me just make this note. This is since we had perfect recovery. That's what we supposed before. So y of t equals x of t. Okay, and so now we see why this is called an interpolation formula, because what's happening is that, let me draw this, it's going to get a little complicated. Okay, let me just draw this real quick. Okay, I'm going to draw it down here because I'm going to write something over it in a second. Okay, but this is going to be drawing x of t because that's what this whole sum equals. So let me just draw x of t in real quick. There's something like that. Okay, and what's happening here is that apparently x of t is actually a big sum of these sinc functions scaled by these numbers. But to draw it accurately, we have to investigate these sincs a little more. Let me just make that as a note. We want to look at what's happening at these sinc functions at these places n t sub s, because that's where these x values are going to come from. So if t is some integer times t sub s, or some integer k, so let's just look at this, then sinc of pi over t sub s, when I plug in that k t sub s for t, I plug it in right there. What does this equal? Well, this just equals sinc of what? Well, the t sub s's cancel, and I just get pi of k minus n. But remember, sinc is just sine of the argument divided by the argument itself. So when is sine 0? Sine is 0 at any integer multiple of pi. Okay, so whenever this k minus n is an integer, okay, then that sign is going to be 0, except when this k minus n equals 0 itself, because remember, sinc of 0 actually equals 1. So we get 1 here when k equals n, okay, when this argument's 0. But for any other time, any other integer, when k doesn't equal n, that sign of pi times some integer is just going to be 0, because sine is 0 at all integer multiples of pi. So what is this telling me? Well, let me draw in, let me actually change this function to tab. Let me draw something like that. Let me draw in where all of our sampled points were in red. Draw them like this. Actually, let's do one there. It's going to get a little complicated, so I don't want it to be too messy. Okay. And these sampled points are at all of these integer multiples of the sampling period. So this will be 0, t sub s, 2 t sub s, 3 t sub s, and so on. Draw this one a little over. Okay. And this is at negative t sub s, negative 2 t sub s, and so on. And now what is happening at each of those points? I'm going to take x of n t sub s, which are these values, and I'm going to multiply them by sinc functions. And based on this discussion, those sinc functions, okay, are always going to be 0 at any other integer multiple of t sub s. So let me draw one of them in, and you'll see what I mean. Let me just draw in the one when t is 0. So I'm going to have a sinc function starting here. And since it has to equal 0 at any other integer multiple of t sub s, it's going to go through the t-axis at all of these other sampled points. Okay, so that's that sinc function. That is this sinc function here, scaled by x of 0. That's when n is 0. Now we have to draw all of these in for all of the other sampled points. It's going to look something like this. Okay, it's okay if our green goes above the black here, because some other sinc function might be subtracting from that. Okay, so it turns out, amazingly, this is why it's called an interpolation formula. These sincs are kind of interpolating between the sampled values in order to reconstruct our original signal. Okay, so maybe I'll stop drawing at this point. Okay, maybe I'll do this one negative one. Okay, so it's true for the negatives as well. Anyway, you get the point. So amazingly, it's bizarre, but if I gave you all of these red sampled points, okay, and I said, put all these sinc functions, amazingly, at these points scaled by the value of x at those points, scaled by the sampled values, and add them all up, you exactly get back x of t. All those green functions mysteriously add together to give you back exactly that black function x of t. It's really amazing. Okay, so we saw in the last video what happens in frequency, right? When we recover our original function from its samples, we kind of extract that perfect copy in the frequency domain, okay, from the Fourier transform of the sampled signal. What's happening in time? This is what's happening in time. All these sinc functions are somehow combining together to interpolate between the red sampled values and give us exactly our original black function here, x of t. Okay, so pretty cool. You see why we start with the frequency domain analysis before we do this, because this is a little strange. But we just went through the math, and this is what we obtained. The main idea being that when we use this low pass filter, this reconstruction filter and frequency, in time we're convolving with a sinc function. And we just followed it through and got this amazing interpolation formula for our function x of t. Okay, so pretty cool. So that's all I have for this video, and I'll see you in the next one.